Project number 3, Inferential Statistics. Let's go to our Statistics Projects file and go to the third sheet. Once again, we'll be working with our business executives data. Let's create our pay variable. Recall that this is going to be high or low depending on whether or not salary is greater than or equal to 81,000. So we'll say equal if, grab our salary, greater than or equal to 81, comma, we want it to say high, and in quotes low. Alright, center that. And drag it down. Can't double click it because of that header underneath it. Okay, now pay D, D stands for dummy. We're going to need to have a quantitative variable based on the qualitative variable pay such that there's a 1 for high and a 0 for low. So we can actually start from first principles and grab salary. See if it's greater than or equal to 81. This time we want it to say 1. Do not use the quotes if it's greater than or equal to 81. Else 0. Again, do not use the quotes. We need this variable to be numeric, actually. All right. So hit center and drag that down, or copy it down, and we see that the low values all have zeros and the highs are ones. Okay, good. Let's save what we've got. Now we're going to need 3 named ranges to make our analysis easier, more convenient. Let's go ahead and hit the print preview to get the dashed lines in there. All right, we can see where the page breaks are. So we need salary. And we'll scope this again to our third project, Inferential Statistics. And we can see in our name range there, right? Again, if we make a mistake, we have to go to Formulas, Name Manager, and just delete the name with an error, named range with an error, and start over. Now we need also pay D. Again, make sure you use the label. Control Shift down, right click, define name, pay D, and scope it to inferential. And we've got 2 up there. Now we need one called data. We're going to grab the entire set of data with the labels, including executive, and call this data. And scope it to inferential statistics. Alright, save what we've got. Alright, let's move on. Now we're going to do 2 different standard types of analyses. One for a normally distributed variable, which is salary in our data set, and another for a Bernoulli distributed variable, pay. Pay is Bernoulli because it's got 2 levels, high and low. Now, each of the variables is going to have a work section right up here, which we'll start with. But let's talk about the assumptions of the analysis here. So for our normal variable, we'll be using salary. And for our one population analysis, we'll be considering all executives. Now, we're assuming unknown variance, so we're going to use the t-distribution. If the variance is known, we would use the z-distribution. For 2 populations, we're going to compare male executives versus female executives. And our variances are unknown, so we'll use the t-distribution. If the variances were known, we'd be using the z-distribution. Now, if variances are assumed unequal, use the standard error with the special degrees of freedom. If the variances are assumed equal, use the standard error based on the pooled variance with the regular degree of freedom. Okay, so now We're going to use some formulas here to fill in this section here of the what I call the work section. And the formulas you can find on the statistics projects formula sheet. It's starting with the third. There's actually 4 sheets for this project. 2 for the normal analysis of salary and 2 for the Bernoulli analysis of pay. So here's our first one. Here's the formulas here. You see here that N will be the count, X bar, mean, S squared, variance, so forth. And when you have a subscript here, the 1 refers to males and the 2 refers to females. So this is the count, or the number of observations for males, the number of observations for females, and so forth. All right, so let's go over here. Now, we need the number of observations for all the business executives. We can use the count function here, and then use our named range, salary. Good, let's go ahead and grab the entire section and make it centered. Center the numbers with 3 decimals. All right, now I want to show you a new function here. What we want to be able to do is count the number of males in the gender column, or actually count the number of salary values corresponding to the males in the gender column. That's going to take a special function, and this is going to be called, it's a database function, and the function is the same, got the same name as the regular function, except you put a D in front of it. So we'll say equal D count, left parentheses. Now the database, that's the data named range. We can use that. That grabs the entire set of data up there. All right. And then comma. Now the field is the column in your data set that you want to do the analysis on. So in this case, it's the second column, and we could put number 2 there, put a 2, or you can put in quotes the column that you want to work with. So we'll do that. Say salary, and then the criteria. This takes a 2 row descriptor, and that's why I put the gender and male up there. So the criteria then is going to look inside the gender column and identify the males, and then count the salary values corresponding to the males in the gender column. So we'll hit, we do not lock that because I'm thinking about copying this over. Right, so we've got 16 salary values corresponding to the males in the gender column, and then we drag this over and we get 19. All right. That allows us to type one function and to copy it over instead of writing multiple functions. Okay, go ahead, do the same thing with mean and the variance, and we can use the average function for the mean, obviously the var.s, and then use the d-average and the d-var for the male and female values. Okay, here are the results, and let me make a comment about the special DF. The special DF looks rather complicated. Here's our formula sheet here, but note that it only involves the male variance and the male count and the female variance and the female count. The challenge is the order of operations here. Note that the n-1 has to get done before being divided into the 1. Same thing with the n2 minus 1. And also, the bottom has to be done, this sum here, before it's divided into the numerator. So, note that. If you're having trouble doing this formula, I would recommend breaking up into pieces, the piece on top, the lower left and the lower right, and then combining those pieces. Once you get the individuals done correctly, combining them back into one formula. And then also, you're going to get 29.262 when you do the formula correctly. That's what you'll see. And then you're going to use the round function with 0 digits to get the 29.000. Okay, and you can go to your formula sheet, or not the formula sheet, the solution sheet, to check your answers. So, yeah, there's the first project, second project, right here. And there it is right there. You can go up to this here and check the section, the work section, check all your numbers. And of course you can check later through all the pages to verify that you're doing it correctly. Okay, so yeah, once you get that done, now we can use these pieces in the work section to fill in for our confidence intervals and hypothesis tests. So we're going to do confidence intervals, and there's a one population analysis and two population analyses, one for unequal variances and one for equal variances. And note here that I've used 3 different confidences, 90%, 95, and 99, which of course translates into 3 different alphas. Now, note that the quantities that change, most importantly, through these sections are the degrees of freedom, and the standard errors. Those are going to be different for each analysis, one population and the two population analyses. I've listed the degrees of freedom in order. See, here's the first one. There's the second one, the special DF. This is appropriate. First one is appropriate for the one population analysis. The second one is appropriate, the special DF, for the 2 population unequal variances. And the third is appropriate, the regular degrees of freedom is appropriate for the 2 population equal variances. That's going to be the same for the hypothesis testing as well. Okay, let's see how to do this now. Now I'm thinking ahead. I want to copy my formulas, so I want to lock certain things and not lock others. We're actually going to lock the DF, the mean, and the standard error. So you can actually put little $signs up here to remind yourself that those are locked right there. So we'll say equal. I grab the first DF, I lock it, and then these are going to be centered without 3 decimals, and these you can center with 3 decimals. So the mean is going to be this mean here, right, for the overall, F4. We'll use the delta mean down here for the 2 different 2 population analyses. So I can grab this right here and say center, and then make sure it has 3 decimals. The standard error is the first standard error, which is right there. This is the one that's appropriate for the 1 population analysis. I lock that. Now the critical T, go over to your formula sheet and get this back to, alright, go to the second page now. These are the formulas down here which we just filled in for the work section. Right? Now, for the confidence interval critical values, this is the function we use, t.inv. So we'll say in here equal t.inv, left parentheses, and we need 1 minus alpha over 2 and the degrees of freedom. So we'll say 1 minus, you grab the alpha divided by 2, comma, and then the degree of freedom. Close it. 1 minus alpha over 2, degree of freedom. Good. Now the margin of error is the critical value, t, times the standard error. So they're right next to each other. Just grab them. And the lower CL is the mean minus, you can see that from the formula sheet, t statistic, sorry, no, that's not on here. The lower limit is the mean minus the mho, and the upper confidence limit is the mean plus the mho. So we'll say equal, grab the mean, minus the mo, and then we'll say equal the mean plus the mo. So we can say then we are 90% confident that the population mean salary is between $79,259 and $84,113. Now we can take this whole thing down here, this whole line, and drag it down, and we see that everything, the dollar signs allowed us to lock the ones that we wanted to remain fixed and change the formulas or change the results of the values we wanted to that depended on the degree of freedom or the alpha, or sorry, the alpha. So we see here now then we are 95% confident that the population mean salary is between $78,769 and $84,603. Note that as you increase in your confidence, your margin of error gets bigger, and therefore you sacrifice precision, and the confidence intervals get wider. Again, there's a trade-off between confidence and precision. The more confident you get, you have to pay for it for less precision, with less precision, and you can see that there, indeed, that's the case. All right, let me show you how quickly this can go. Now, we're going to use the second degree of freedom here. So I'm going to grab the special DF, lock it, and we can just make sure we get this with no decimals there. Now the delta means is the difference, and we want to lock that. And let's make sure these have 3 decimals and centered. Standard error is the second standard error, right there, the 2.164, lock that. And the critical T is the same formula. So what I can do is I can just copy this down right now. I can grab this whole section, Control C and Control V. Excellent. And save what we're doing. Now the interpretation of the two populations is that we are, this first one here, we are 90% confident that the difference in means, that is the male mean salary minus the female mean salary, is between $7,839 and $15,194. Right, so since the difference is positive, we're taking male mean minus female mean. The male mean is larger than the female mean with 90% confidence anywhere between the two numbers that we mentioned. And again, we see as we gain confidence from 90 to 95 to 99, we lose precision. The margin of error gets bigger, and therefore the confidence interval on the difference in the population means gets wider. Now you can do the same thing here with this degree of freedom. This is the next, or this analysis, get the next degree of freedom, use the same delta means from above here, difference, delta means difference, get the third standard error, and then you can copy that section down. So go ahead and do that. Okay, here are the results, and recall that you can go to the statistics project solution to see, verify that your numbers are correct. All right, now for the hypothesis tests, again we have the same 3 analyses here, a 1 population analysis and 2 population analyses, one for unequal variances and the other one for equal variances. And we've done form A, B, and C, what I call form A, B, and C, where this is mu greater than or equal to 85. Now 85 I put in green here because it's a flexible value. You can change that. I've chosen 85 in this analysis here. The second one, this would be what's called a left tail test. This would be a right tail test, and then a two tail test, form A, B, and C. And I've also utilized 3 different alphas. So we get 9 different analyses in each of these sections. Okay, again, the degrees of freedom are going to change in the same way that they did for the confidence intervals. So this is the first degree of freedom up here. second degrees of freedom, the special DF for the unequal variances analysis, and the regular DF. And you'll see the mean and delta means are follow the same pattern. The standard errors are going to change again as well. I'm going to copy actually cut those. And then these are the ones that are locked. So let's see how this works. So we'll say equal. Now, a lot of copying and pasting here. Grab the first DF, lock it, and center it and use 0 decimals for that. The mean, again, for the one population analysis, the overall mean is the appropriate value. And center and use 3 decimals. Standard error, we want the first standard error. That's right here. Lock that. And the t-statistic, now go to your formula sheet. We see the t-statistic is the sample mean, or the delta means in the case of two population analysis, minus the hypothesized value divided by the standard error. So we'll say equal, it's the left parentheses, the mean in this case for the two population analysis, we'll be using the delta means, minus the hypothesized value, parentheses, divided by the standard error. Now look, I can't click on the standard error box, it's kind of hidden, so I click somewhere else and then just move the box underneath there. Alright, so we should get minus 2.309. Alright, so this form A here is a left tail test, so we need a lower critical value. So where do we get that? You can come over here and you see that we're going to use the t.inv function with alpha and the degrees of freedom. So we'll say equal t.inv, grab the alpha, comma, and then the degrees of freedom. All right. Now you can actually drag these down and go ahead, complete. Well, I'll do the p-value first with you on this one. So the p-value is going to use, there's 3 different ones, just like there's, depending on the form A, B, or C, just like there are different combinations of upper and lower critical values for 3 different ones. Okay, so here we go. This is going to be the t.dist function, the t-statistic, degree of freedom, and true. So we're going to say equal t.dist, parentheses, and the t-statistic, comma, degrees of freedom, true. This is the area under the curve to the left of the t-statistic. Area under the t-distribution, t-curve, with 34 degrees of freedom to the left of the t-statistic. It's a left tail test, so we have to go to the left. Right? T-statistic, degrees of freedom, true. All right. And you should get 0.014. Now, the rule is that if the p-value is less than the alpha, you're going to reject, else accept. So we'll say here equal if, parentheses, p-value less than the alpha, and then we're going to say reject, else, we'll say accept. All right, and then center that. Okay, go ahead and fill in for form B and form C, and then what we can do is take this whole section here and copy it down. So go ahead and fill those the rest of those in. Okay, here are the results, and now I can just take this whole thing here, Control C, oops, grab it right, Control C, Control V, and Control V. Good. So you see here the left tail test that the population mean salary of all the business executives is greater than or equal to 85 is rejected because the p-value is 0.01. But the right tail test that the population mean is less than or equal to 85 is accepted because the p-value is 0.986. And the two-tail test that the mean salary is equal to 85,000 is also rejected at 10% because the p-value is 0.027. And then you can move on through these and interpret them in a similar fashion. Notice that we reject the two-tail at alpha of 10%. We reject it at 5%, but we do not reject it at 1% of an alpha of 1% because the p-value is 0.027. All right, now you can go ahead and do the same thing for two population unequal variances and the two population equal variances. Okay, here are the results then for the other two hypothesis tests, the two population unequal variance and the two population equal variance. Again, go to the statistics projects solution file to check your answers. Okay, now we're going to do some equivalent two population hypothesis tests. So we're going to reproduce the unequal variances for two populations and the equal variances using Excel's data analysis tools. So in order to do that, we need to get the data in the form that Excel needs, and we need to have it in columns. So we need the male salaries here and the female salaries here. The way I do that is go up here. Now be very careful. Grab the entire range, and I want to sort the data. Go to Data, Sort by Gender. All right, I got the females first. Now I can go ahead and grab the female salary, right-click, copy, paste that right here, and then I can go up and grab the male data and paste it right here. Good. Now I'm thinking ahead. I'm going to need to do the same thing when I get to the pay section, and I want to be using pay D. So why don't I go ahead and do that while I'm at it? Go here, right-click, copy, and then go down here. Right here. Good. This is the female. Now we need to use paste special because remember we had formulas inside that variable, and if we copy the formulas, the cell references will be off. So we're going to say values and number formats, or just values would do, but I'll hit values and number formats, and then we can hit center. If I would have pasted just use a regular paste, it would have been all zeros because the cell references would have been off. All right, let's go up here and do the pay, or the males. So that was the females. Okay, here's the males. Right-click, copy. Paste the males. Paste special. Values and number formats. Good. Now let's go back up and resort everything by executive. So again, grab all the data with the labels, go to Data, say Sort, and then by executive. Good. Let's save what we've got. All right. Okay, so up in here, we want to do a t-test assuming unequal variances. So go to Data, Data Analysis, and we see down here the t-tests. There's a t-test 2 samples assuming equal, and there's one for unequal. That's one we use first. And there's also, we're going to use this paired, and later we'll use the z-test 2 sample for means. So right now, it's the first one, unequal. This is the one that utilizes the special degrees of freedom. So variable 1, we grab the males with the label. Variable 2, grab the female with the label, female data. Now the hypothesized mean difference. This is the value that we're using in this project. You know, we want to be able to reproduce the exact same results, so we have to put in a 5 here. This is the null hypothesis is the difference in the means of males and females is greater than or equal to 5. That's form A, form B, less than or equal to 5 and equal to 5. So the first one is a left tail test, second one is a right tail, and then it's a two tail. So we have to type in a 5 here. And then we did use the labels. In the output range, once in the circle, once in the open box, and click in 118 here, and then hit go. All right. Now grab our numbers here, go center and use 3 decimals, and let's green and bold, use the green here, and bold the hypothesized mean difference, because that's the number we chose. That's flexible. And then go ahead and grab the t-statistic, make it red and bold, and then we can verify. See the 3.00311 matches the 3.011 we did right there. And then the two-tail p-value 0.005 matches up exactly with the two-tail 0.005 right here. And this is a left tail test, so the 0.003 should match the left tail, and there it is right there. Actually, that's the right tail test. Yeah. 0.003 matches that one. Okay, so now go ahead and do the next one. Do the let's write the conclusion in here. Now look at the p-value for the two-tail test, 0.005. It's less than the 5. The typical alpha is 5%. So we'll run the test at 5%. Since this is less than 5%, we reject the null hypothesis that there's a difference in means of 5, right? That the male mean minus the female mean is equal to 5. We reject that. So we're saying here, reject the hypothesis of a difference in means of 5 at 5%. And that's red and bold that. And you can save. So go ahead, run the t-test, two-sample, assuming equal variances, and write your conclusion. Okay, here are the results. See we green and bold the 5, the hypothesized mean difference, red and bold the t-statistic, and we see that the t-statistic indeed matches up, and the p-value, two-tail, two-sided, 0.004 matches precisely. And also note that in the first analysis here, the special DF, the 29.000, that matches the 29.000 that we had to write that complicated formula for. So this gives you that result in a very easy manner. Of course, now the advantage of having put the program the values is that, again, like in project number 1, when the data changes, all the programmed cells will update automatically. These analyses will not. They're not connected to the data. You'd have to if the data changed, you'd have to rerun these analyses. So this one, if you only need one analysis, is very good. But if you need something that's flexible, that will update automatically when the data changes, then it's much better to do the more powerful approach that we've done up here. Okay, now there's a couple other tests here that are important that I want you to do, and you can do them on your own. The first one is an F test, two-sample for variances. What this is, it tests the null hypothesis that the variances are equal. Now, If you reject that hypothesis that the variances are equal, then the two population analysis for unequal variances would be appropriate. If you accept the hypothesis that the variances are equal, then the two population equal variance analysis would be appropriate. So this is the F-test two sample for variances, and you can get that by going up here to data, data analysis, and they're in alphabetical order. So there's the F-test. You're just going to grab the male data and the female data with the labels and change the output range to A151 and interpret the result. Again, if the p-value is less than alpha, you're going to reject the hypothesis of equal variances. If the p-value is not less than alpha, you'll accept the hypothesis of equal variances. Okay, and then the final analysis underneath that is a t-test paired for means. Now this is quite a bit different than what we've been doing. I'll look up here at the data. Instead of comparing male executives versus female executives, we're going to put all the executives, look at them all at once, but compare salary to versus salary. So you can think of it more of as a horizontal analysis rather than a vertical analysis. And so each person, each executive has two values. That's what's called a paired analysis. And we're asking basically whether is salary 2 different than salary 1? Or are the differences between salary 2 and salary 1 on average equal to 0 or not? So when you run this test, you're going to, it's up here, let me show you the data analysis. This is at the bottom here, the t-test paired two sample for means. And in here you're going to use salary 2 and salary 1. All right, and then the hypothesized mean difference will be 0, and you check labels and then change your output range and interpret it that way. If the p-value is less than alpha, you're going to reject the hypothesis of no change from salary 2 to salary, and we're going to use 5%. If the p-value is greater than alpha, you're going to accept the hypothesis of no change at 5%. And alpha is we'll use 5%. That's the typical alpha. Okay, so go ahead and run those analyses. Okay, here are the results. My F-test for variances. The p-value is 0.225, so I accept the hypothesis of equal variances at 5%, and the conclusion would be then, or the result would be that I would choose the equal variances analysis over the unequal variances analysis. And here, comparing salary 2 to salary, I make green and bold the hypothesized mean difference of 0, and the red and bold the t-stat, and I see that my p-value is my two-tailed p-value is 0.033, and that's less than alpha, so I reject the hypothesis of no change, no S in there, no change at 5%. In other words, salary 2 is definitely different than salary, so either an increase or a decrease, but I see that salary 2 is above, the average salary 2 is above average salary, so I would conclude that there has been an increase from salary to salary 2. All right, now the next section, this is pay. Now this is our Bernoulli random variable. Again, for one population, we're going to use all executives, and we're going to consider all executives. Now it must be the case that n times p, that's n is the number of observations, and p is the proportion of high salaries, is greater than, or high pay is going to be, has to be greater than or equal to 5, and n times 1 minus p has to be greater than or equal to 5. And we'll always use the z distribution. Now the sample size, the n times p and the n times 1 minus p condition is important because we're going to invoke the central limit theorem, and we have to have a large enough sample size for that to be appropriate. And the rule for the Bernoulli is n times p and n times 1 minus p have to both be greater than or equal to 5. Now for the hypothesis test 1 population, there's a special case here where we use the hypothesized value in calculating the standard error. That's because when you do a hypothesis test, you assume that the null hypothesis is true, and if that's the case, then we're going to use the hypothesized value when we calculate the standard error. You'll see how that works down below. For two populations, again, we're going to compare male executives versus female executives. Now, the sample size rule has to be the same for both or has to be larger. The sample size has to be large enough for both populations. And again, we always use the z distribution for Bernoulli. Now, last special case here for hypothesis tests for two populations, when the hypothesized value is 0, that is the difference in the value, the means are assumed to be 0, then the variances are presumed to be equal. That's because if the proportions are different, the difference in proportions is 0, that means the proportions are equal. And if P1 equals P2, then P1 times 1 minus P1 is assumed to equal P2 times 1 minus P2, and therefore we use the standard error based on the pooled variance. That's the only time that there's such thing as a pooled variance, is when the hypothesized value for two populations is 0. Okay, so once again, we're going to use our formula sheet. This time we're on the Bernoulli 1, and again, subscript 1 refers to male, the subscript 2 refers to female. Note that there's a difference here from the salary. The variances are calculated not using the normal var function, but using the previously calculated proportion. So it's P times 1 minus P is the variance for the Bernoulli. All right, so that means we're going to use the D count for the n, the D average for the proportion. Remember, the proportion is just the average of the ones and zeros. So it's the same formula, average, and then D average for these two. So, but for the variance, we're not going to use the var.s function. We're going to use the P times 1 minus P. Okay, so go ahead and fill the workhorse section in. Again, those are the values that are going to be used to fill in the confidence intervals and the hypothesis test. Okay, here are the results of the work section for pay, and note that I've used 4 decimals here on the male and female variance and 4 decimals for the pool variance. We're going to need that later. We'll need that accuracy. Also, I forgot to mention up at the top here, there's a common mistake, or a mistake easy to make. If you accidentally type a space, let's say after the male, right, the numbers, everything looks fine up here, but your functions won't work because of that space. So go, if it's not working out, go up here, check to see if you have spaces anywhere. The gender may have a space on it. That could mess things up for you. Right? So be very careful. It's easy to type a space. Also up here, pay D, make sure that you don't have a different formula at the top or different named range, or actually, in this case, this is not a named range, but this has to match exactly what's up at the top here. Pay D has to be written. There can be no space there, and so forth. Okay, let's see how the rest of this works. Again, you can, to check your answers, go to the Statistics Project solution file to check your answers. So here, there's only 2 types of confidence intervals. There's no such thing as an equal variance, like I mentioned up here. The only time up here in the descriptions, the only time there's an equal variance situation is when you're doing a 2 population analysis and the hypothesized mean difference is 0. That is the difference between the proportion of males with high pay and females with high pay is 0. In that case, PM equals PF, and therefore PM times 1 minus PM equals PF times 1 minus PF. So this then is the proportion. We grab that right there, lock it. You want to lock these two. Alright. So, these all. Alright, standard error is the first one. Again, they're in order, so that one goes first. And we can, critical Z, go to your formula sheet and see that the confidence interval critical values is norm.s.inverse.inv 1 minus alpha over 2. So this is norm.s.inv. This is the standard normal curve. So it's 1 minus alpha, comma, and no comma, just 1 minus alpha. Yeah, that's all you need. 1 minus alpha over 2. Alright, and then no dollar sign on that one. The margin of error, again, is equal to the critical value times the standard error. And the lower CL is, again, the mean minus the MO. Now, the mean in this case is the proportion, right? Remember, the proportion is a mean of the ones and zeros minus the MO. And we say here equal the mean of the proportion plus the MO. Now, so we can say here that we are 90% confident that the population proportion of high pay is between 37.5% and 65.3%. Now we can drag this down. Once again, we see that as you get more confidence, up to 99%, you get less precision because the margin of error is increasing. So we're 99% confident that the population, that is the proportion of all the business executives with high pay, is between 29.7 and 73.2%. That's much less precision than the 90% confidence limits. Okay, now here you can just change go to delta proportions. That's a difference in the proportions. Lock it. Lock the standard error, the second standard error, not the third one, the second one. And then center this, drag this down, and you can take this whole thing here, Control C and Control V. Good, save it. Now the interpretation of the difference here is that now we say that we are 90% confident that the difference in proportions between the males and females, the proportion that is with high pay, is between 31.8% and 78.0%. So the males, we're 90% confident that the males have a larger proportion high pay than females. Okay, now here, this one is a special case. We see up here, like I described, that for one population hypothesis test, we assume that the null is true right here. So we want to use this value in calculating our standard error. So you're going to put a dollar sign here. There's a dollar sign here. But this is a little different. So this is going to be equal to this proportion. Lock it. Now the standard error, so we're going to say equal SQRT, grab the hypothesized value, no dollar signs, times, parentheses 1 minus the hypothesized value, no dollar sign, divided by the count, overall count, and lock that one, end parentheses. Good. Now make this bold because it's different. It doesn't follow the pattern. So make that bold. This is the only one we have to do that to, though. The other ones follow the pattern. The Z statistic, again, you can see from your formula sheet, is either the sample proportion for the one population and hypothesis test, or the delta proportions, the difference in proportions for the two population tests, minus the hypothesized value divided by the standard error. So I'm going to grab here, grab the proportion, minus, which is the same as the mean, right? Minus the hypothesized value divided by, again, we can't click on the standard error in the box we want, so click in a different one and move it up like that. No dollar signs. Good. Drag this down for now. Later we'll be able to take this whole thing and copy and paste it. So the critical value, again, this is a left tail test, this is a right tail test, and a two tail test. So we need, for the left tail test, we need a lower critical value, and that's gotten with the norm.s.inverse function. So we'll say norm.s.inverse, and that's just alpha. And the p-value, the first p-value for form A is norm.s.dist equals norm.s.dist and z statistic and true. So left parentheses, grab the z statistic, comma, true. Since this is a left tail test, this is the area under the curve to the left of a standard normal distribution to the left of the 2.038, and we get 0.979. Again, the rule is you're going to look at the p-value and see if that's less than alpha. If it is, you're going to reject the hypothesis that p is greater than or equal to 0.35 or accept it. So we're going to say equals if p-value less than alpha, comma, reject, comma, accept, and center that. Now, I didn't mention this above, but there's two ways to do this hypothesis test, right? The p-value approach is what we used, but you can also compare the z statistic to the critical value. If the z statistic is less than the lower critical value, you reject. And it's clearly not less than that, so we accept, but the p-value approach and the critical value approach will give you the exact same thing. Now go ahead and fill in the rest of them. Once you do that, you can copy and paste that whole section. Okay, here's the results of that first section. And I could just take this here, Control C. Oop, doesn't like that. Control C, Control V, Control V. Excellent, I can get rid of these right now. Don't need those. Oh. Clear contents. Alright, save it. Now this is the only one with the bold. So go down here, fill in the rest. Note that the delta props changes from the proportion, and the standard error will change. This one now becomes the 0.140, and then this one right here becomes the 170. This is the only one where you actually use a pooled standard error based on a pooled variance. Right. Remember, there's a lot of copying and pasting on this, so go ahead and fill that in. Okay, here are the results. Now for the two population, this is how the interpretation goes. This is, we'll interpret this one. This is a left tail test, form A. So we see here that we accept or fail to reject the null hypothesis that the male proportion of high pay minus the female proportion of high pay is greater than or equal to 20%. However, the right tail test, that the difference in the proportions between males and females, that is proportion with high pay, is less than or equal to 20%, we do reject. See, the p-value is much less than alpha of 10%. Okay, now we're going to do the equivalent two population hypothesis test, that is the unequal variances and the equal variances. So recall that we use a z distribution always for Bernoulli's. So we can get Excel to do this by going to data analysis down at the bottom. We've used the paired and the t-test for equal and unequal variances. Now we're going to use the z-test to sample for means. Alright, we can grab the male data up here, grab the female data, and then the hypothesized mean difference, we have to use the value that particular value we used up here in order to get the results to match up. And notice that we used the hypothesized value is 20.2, so we have to type that in 0.2. Now this routine was set up under the case where you know the variances. Remember, that's another situation where you use the z, is for the normal data like salary when you know the variances. But we're going to use this routine, and for the Bernoulli, where the variances are unknown, but since we always use a z distribution for Bernoulli, it'll work out. But instead of putting a known variance in here, we're going to use the sample variance, but we need to put enough accuracy in there to get so we don't have round off error. So that's why I put 4 decimals up here. So for the known variance, we're going to put the point for males 0.1523. For females, it's 0.1939. Right? 1523, 1939. Check the labels box, output range, click once in the circle and then once in the open box, and then click right here and hit OK. Good. Now go ahead and grab these, and then let's put green and bold, make those 4 decimals. Green and bold the known variances, that's what we plugged in, right? And then green and bold the hypothesized mean difference, that's something else we chose. And then red and bold the hypothesized mean difference. Notice that the 2.487 matches up perfectly with the 2.487. The p-value for the two-sided form C is 0.013. So we say again down here, then, since the p-value is less than alpha, we reject the hypothesis of a difference in proportions of 0.20 at 5%. Good, let's red and bold that one and save it. Good. Now go ahead and do the z-test and replicate the equivariances. Now note there's 2 differences. The hypothesized mean difference is 0, not 0.2. And also now the known variance, instead of plugging in the male and female variances, you're going to use the pooled variance for both. All right, the 2.498. So go ahead and do that, and you'll get your results. You'll know if you did it correctly. If your results match, you'll get the z statistic, the same p-value, and so forth. So go ahead and run that one. And here are the results. See, my p-value is 0.001, same as the p-value up here. So we reject the hypothesis of equal proportions at 5%. Finally, we're going to run the test of independence. First, together we're going to do test independence of gender and pay, and then you're on your own going to test the independence of education and pay. So we're going to start off by using a pivot table. So go here, say insert pivot table. Now remember, from project 1 we grab all the data including the labels, kind of a strange step, and then we hit OK. Yes, now I'm thinking ahead. Before I put my variables into the table, I want to make sure that Excel does not change my column widths. So I go up here to Options, open that up, say Options, okay, go to Options, and then uncheck the auto column widths on Update. Good. All right, let's put the gender in the rows, the pay in the columns, and then the executive in the sum values section. And again, we don't want to sum up the executive IDs, we want to count them. So we open up, say value field settings, and say count. Right? Value field settings, say count. Good. Now I can go overhead here and center that. And actually, I don't like all this formatting, so we'll go to Design, open up the choices, use the light, the basic, and up here I can call this Pay, center that, and then call this Gender. All right, good. And these are the observed frequencies. I'll put a little title there. Good. Now we want to assume independence and therefore calculate the frequencies that we would expect if they were independent. So what I do is I copy this thing here, just a shell actually. So I only need this part. And put pay up here. Yeah, and so I don't need this, so I can clear this out. And merge and center that. Clear out. Don't need the grand total down here either. Good. So I'll use the border for that. Don't like it on the inside. And just go to the outside here. One more. And then clear the numbers out. Excellent. Do one more right here. All right. Now, we're going to calculate in here the expected frequencies. And all should be, we can insert a symbol here, insert symbol. Greater than or equal to 5. All right, now remember that the rules of probability state that if two things are independent, you can multiply their probabilities together to get the joint probability. So what that involves is that actually in here we can calculate the probability of a female with high pay is the probability that you're a female times the probability that you have high pay. And then we want to actually convert this into a count. So we'd have to multiply those two probabilities one more time by the overall count. So what that results in is then it ends up being the count inside this cell under the assumption of independence is the column total time, or the row total times the column total divided by the grand total. So we can say up here equal this one. Now I'm thinking ahead, I want to copy this over but not down, or over, and I don't want this to move to the right, but I do want it to move down. So I'm going to lock the letter. Right. And then multiply by the total here. Now this one I want to lock the column. So I lock the number. and then divided by the grand total. I don't want to lock, I want to lock that in both directions. So this way I can write one formula in here. Okay, so this is going to be use one decimal. I got 9.8. I can drag it down, and I can drag these two over now. So these are the accounts that I would expect, and I can get rid of the inner border and just use the outer border. Good, so these are the counts I'd expect if gender and pay were independent. I'd expect to get 9.8 females with high pay, 9.2 females with low pay, and so forth. Now, the difference between the expected and the observed, or the observed from the expected, gives me the degree to which there is dependence, that they're not independent. So let me copy this down here. And we want to calculate those differences. And then, yeah, so I can clear this out right now. Clear contents. Save what we're doing. Now, the rule here is that these are called cell chi-squares. And this will be the observed minus the expected squared divided by the expected. So we say equal left parentheses observed minus the expected squared divided by the expected. All right, good. Drag that down and over. Good. And clear out the center and then put the box back in it. All right. So now to assess how far away the observes are from the expecteds under the hypothesis of independence, we can just sum up this chi-square statistic. We can just sum up the cell chi-squares. So use the sum function, grab everything in there, and then center in 3 decimals. And we can red and bold that. And then we calculate the degrees of freedom, and then finally the p-value. All right, for the degrees of freedom, this is the number of rows minus 1 times the number of columns minus 1. So we say here, and I'll show you a nice function here, rows, grab this whole thing, minus 1 star columns, this whole thing, minus 1. Good, hit center. And finally, we want the area to the right of the chi-square statistic, the area to the right underneath a chi-square distribution. So we can use 1 minus chi-square dot dist, left parentheses, grab the chi-square statistic, the degrees of freedom, and then the cumulative is true. All right, so we get 0.001. Oh. Use 3 decimals, and so we say here we reject the hypothesis of independence at 5%. See, the p-value is less than 5%. Red and bold that. In other words, the chi-square statistic is too big, the cell chi-squares are too large, if indeed gender and pay were independent. All right, so go ahead and do the test of independence for education. What you can do is copy this whole thing down here, save yourself some time. On the inside here, now swap out gender, take gender out, put education in instead. Excellent. And you get your table, and drag this down, and then you can go and do the rest on your own. Actually change this now to education. Okay, so go ahead and do that on your own. Finally, here's the results of the test of independence for education by pay. We get a chi-square of 10.677, 2 degrees of freedom, and p-value 0.005. So once again, we reject the hypothesis of independence at 5%. Again, finally, recall that you can check all your results, or you should check all your results against the statistics project's solution file. Taking a second here to load up. It's project 2. Okay, here are the sheets for project 3. All right, that completes project 3.